So we are back, and now it's time to find the winner of the T-shirt and the mug. And the thing is very difficult because actually nobody explained that. That means that we need to do the videos better and provide more details also. But I think that there has been many people getting close, but not really. So I think that what I'm going to
we have many answers, and now we're trying to find the closest one.
So I think it's the one that mentions about is an algorithm. Well, it's a embedded device that you have algorithms for intelligent control that you can put in any robot. And then you will make your robot intelligent using those algorithms. And then I found one. So I have to check it because I cannot figure out now. The chat is getting down and I cannot mark the first one. And there are a lot of answers. So let me do one thing. I'm going to check this while the next speaker is speaking, and I will provide the winner later.
Mm-hmm. We will have a winner.
Yes.
Okay. So let's moving, right?
Yeah.
Okay, so our next keynote speakers are Bence Magyar and Denis Stogl. Okay, so Bence is a research scientist from 5AI, and Denis is a robotics consultant. In their talk, we will learn how to go from ROS control to ros2 control.
Exactly. So they are going to provide us with some examples of how to create a ROS controller in ROS1, and then how to change this controller or how to create another controller for ROS2, doing the same task, but in a ROS2 way. So Bence and Denis, are you ready?
Hello.
Yeah.
Great. So here the audience is all yours. I think that you are going to start with we are going to start with Bence, and then Denis is going to take the lead afterwards.
That is correct. Thanks very much.
Yeah.
All right. First of all, thanks very much, guys, for being here and inviting us. Today, we're going to introduce you to probably the most widely used control framework in ROS control. It provides a framework for implementing and managing robot controllers with a focus on both real-time performance and sharing of controllers in a robot-agnostic way. The project itself has been around since 2012, or maybe even a little bit earlier. And you can see our cool logo on the top left. And received many contributions over the years from different companies. But I would just like to highlight that one of the major ones was Robotics, who contributed a lot in the early days, and also up to this day. So this presentation is going to introduce you to the basic concepts of ROS control, and we're going to also go through a set of exercises covering how to work with the hardware abstraction layer and how to implement and modify a controller, both with ROS control in ROS Noetic and with ros2 control using ROS Foxy. So it's going to be a complex presentation. Hold on to your chair, strap in. For these demos, we're going to use a 2 degrees of freedom, very simplistic robot arm, as you can see in the notebook. But I put here for motivation. I put a couple of more complex robots here that we can discuss a little bit about these later towards the end of the presentation. But just for you guys to know, all of the robots that we have in this in the table down there use ROS control both in the real hardware and for the simulations. All right. So today's presentation is going to be presented by me, Bence, and Denis. We have both done a PhD in robotics, probably hold different official titles, but it doesn't matter. I've been a fairly active member of the ROS community for almost 10 years now, and I think this is similar for Denis as well. I've been like the main maintainer of ROS control and ros2 control for quite a while now. And currently I'm working at 5AI, which is a company working on different self-driving vehicle technologies. While Denis has recently finished his PhD in control and manipulation, and he's currently one of our most valued contributors and maintainers over at ros2 control. So, with that being said, let us guess.
Bence,
Yes.
there is the mic of somebody. I suspect that maybe Dennis mics that is generating some noise.
Yes.
Okay.
Dennis,
If you
can you hear
mute it,
us?
thank you. Thank you.
I think he's muted now. Okay.
Great. Yes, there is no more. Thank you.
All right. Yeah, so let's get started with the introduction of the concepts. So let's say that you have a great app for a mobile manipulator robot, and you would like to use the navigation stack for controlling your mobile base, and you would like to use Move It for doing some motion planning with your robot arm. The good thing is that both of these planning stacks will be able to talk to a controller with using some well-established, typically ROS topics to talk to some controllers. These controllers, in this use case, are managed by ROS Control's controller manager. You can see the box here. Everyone can see my cursor, right? I'll take that as a yes. So the controllers are managed by the ROS controller. The controller manager, which provides a set of ROS services to manage their life cycles. The controller manager also ensures that only controllers of the right type can be loaded, and that controllers cannot claim the same joint handles to avoid situations that may lead to dangerous movements or harmful events, both for people and robots. The control manager also provides the controller's handles to these resources that they request. These are essentially, it's going to get a little technical here. These are essentially double pointers in C++. And there are 4 main types of them. There's joint position, joint velocity, joint effort. And then the 4th one, which is a bit of a wild card, joint state, which is a special read-only version. These handles are provided by the hardware abstraction layer, which you often refer to as robot hardware, following the C++ class that we use to implement this. A simple setup would typically have 1 robot hardware per real robot, and then there's a general one that almost everyone uses for their gazebo simulation with ROS control. And this robot hardware implementation is very intelligently trying to pick the right components out of the URDF. And it basically serves a robot hardware that is based on the robot description. Following this, one of the major selling points of ROS control is that simulation essentially comes for free, thanks to this component. So if you implemented everything with your robot with ROS control, then putting this into simulation with Gazebo is very, very straightforward, and you don't have to change anything. So let's take a look at an example of controllers and resources. On the left side, we have 3 controllers: base controller, ARM controller, and ARM1 controller. These are, in this example, let's imagine that they are already loaded in the controller manager. This means that they have been initialized and are ready to be started. When we start a controller using the ROS service call to the controller manager, these controllers are given the requested joint handles, which provide them access to the robot hardware's underlying joint state and joint command structure. This structure is depicted on the right side here. The structure itself can be completely arbitrary. It is entirely up to the person who's implementing the robot hardware for that specific robot how this is represented. It could be vectors, it could be specific structures. It could just be a canvas. Well, it'll be a bit of a stretch to do it directly. But let's imagine that for our use case, this is a simple array. So it's just a slice of memory, and the different sections in it represent one double. So also note that the ARM, so in this case, if you see these dashed line and the solid line, highlights that ARM controller and ARM1 controller have a conflict in their resource claims. So both are trying to claim the position joint interfaces of ARM1 joint. This means that only one of them is going to be allowed to run at the same time. The figure also shows that even though wheel 1 joint up here at the top is requested by the base controller, the fields are still accessible through the joint state interface, which I mentioned earlier, which provides read-only access to anyone who wants to have access to this without causing any conflicts between controllers. The joint state interface is typically used by the joint state controller, which is a bit of a special controller. It's not really a controller. Its main job is to publish joint states, which is then used by the robot state publisher and a couple of other components down the line to create the TF tree, and essentially so that we can end up with a visualization in RViz and some other things. So the next version of this figure is just a slight variation. Shows what fields of the velocity joint interface of wheel 1 joint reference to. So you can, if you compare it to the previous one, you can see that the joint state interface is able to read the position, velocity, and effort states. It doesn't really say state there, but those are referred to states. While the velocity joint interface will give us access to position, velocity, effort, and the velocity command. So these are the main differences between these. The framework itself also supports joint limits enforcing, as well as adding an additional layer from joints to actuators, implementing certain formulas of mechanical transmissions, if necessary. But we're not going to go into details on those today, because Ricardo asked us to keep this presentation for only 40 minutes. All right. So without further ado, let me just show you guys the robot that we're going to use in today's presentation once again. Let me get rid of these pop-ups. There. All right. So currently, this one doesn't run anything from ROS control. This is only to show you guys the URDF of the robot. So we have the joint state publisher running in the background, which gives us these nice sliders when launched with the UI. So you can fake that there's a robot hardware in the background publishing some joint states. This is what I wanted to show you guys now. And I am going to pass it over to Denis now, who's going to introduce you to some technical details and some more demos.
Hi, also from my side. So let's talk now more about how to use ROS control with robot hardware, and then later also how to use ROS2 control to enable your hardware. The main idea behind this is always the same. You have to create and load URDF model of your robot. We created this one, a nice RRBot model. Bence showed you already. Then we have to establish controller manager services, interfacing basically through the ROS world, so that you from ROS can send commands from other nodes. And then main part of ROS control is altogether the main loop, having read, update, and write methods. In read method, you read your states from robot hardware. In update method, all the controllers are updated and new commands for the robot are calculated, which are then written in the write method. So let's see how this robot hardware could look like. So we have here robot hardware interface. Each robot hardware interface in ROS1 has to implement hardware interface robot hardware, and implementing this template, we have to also have few mandatory methods. Those are init method, read, and write method. In the init method, you basically initialize parameters of your robot, you initialize your joint handles, your robot has all the memory allocation and stuff like that. In the read method, you will then read the data from your physical hardware, so do all the communication related stuff to read data, and then also in the write method, you will write it. Of course, in read and write method, you should try to avoid any memory allocations or some unnecessary output because you want to keep them as short as possible, as fast as possible, so that you don't, that you can always keep the timing of your update loop short and feasible. Also, this class will have some internal members, of course, like state interfaces. You have to store them somehow, and you have to provide controllers access to those interfaces. So for this, we are using joint state interface, and also somehow you have to receive commands, and for this, position joint interface is used. Of course, for internal storage, to store some values, as Bence mentioned already, usually you will use vectors or something like that of type double when you store stuff. And for example, you can have also additionally members. We have here one example. This is joint names when we are reading joint names from parameter server. And this leads us directly to CPP file. That actually the first thing we are doing, we are reading parameters. In this case, just exemplary showing reading joint names. We are actually enabling in this example users to arbitrarily determine joint names used of their robot. Of course, these joint names have to be then propagated through all the system. You have to keep your names, of course, the same all around. Then you would initialize your joint handles, and of course also initialize variables, and not only initialize them, but reserve memory for them. And usually as default value, we often recommend use none, because don't forget in robotics system 0 and -1, for example, which is often used as in software engineering, like a non-determinate value, it's usually feasible joint state. So you actually want to have some undefined state, and none is then perfect for this. So you can always know if this value is something you want to send to your robot or not. In the read method, we are keeping this very short. We are doing this some outputs just for exemplary purposes. Actually, you want to avoid outputs there. We are not doing nothing special here. We are just outputting what are our joint states. And then in the write method, we are from commands received from the controllers, we are calculating new joint states. This is something which would happen in the hardware in normal use case, in not simulated use case, and these joint states or states variables you want to fill in your read method. Here is just for exemplary purposes. We have to do it somewhere, and then we did this calculation in the write method. So this is how our hardware interface is defined, and then let's see how we can actually use it. In ROS1, you have to implement also your ROS node, taking care about all of this. So as you know, you have to init your ROS node as always first line. You would initialize then some other node handles which you probably need. And then first you have to initialize your hardware interface, and then give this hardware interface in the constructor of the controller manager. So controller manager and controllers has the access to the memory and to the variables of hardware interface. Then you would initialize your hardware and start the main loop. We decided here to use simply ROS rate. You can use some other timing methods as you prefer. And basically, while there is no shutdown or kill command to the ROS, we do the following. We read the data from our hardware. Of course, if some error happens, in the reading of data from the hardware, you always want to stop your controllers, stop ROS control node, because you cannot know what is happening and you can send wrong values to your robot. So this is often good to check if you have valid read, and if not, then you should stop everything. Then you would update controllers if everything worked fine with reading. And after updating controller values, you would write the new values to the robot. So let's launch this example and see what is happening here. So now you can see we also started ROS directly with our robot hardware. This is our robot hardware giving output in the read method as I show you. And also with this example, we automatically also started joint state controller, which should you always start, providing then publishing data to joint topics. For example, here position given 0, all other values are none, as we initialize them to none values. And here this topic is then accessed by all other nodes, as Bence explained you just shortly. Okay, so we have now hardware working, we have our control loop, but wait a minute, there are missing controllers. So let's implement some controllers for this, so we can also move the robot. Because what's the purpose if we have sending robots? Yeah. So controllers in ROS control have to implement controller interface, where you also specify the type of the writing interface of the command interface. We want to have position command interface. And you see in their init function, controllers are receiving access to this interface of the hardware. Then we also have mandatory starting method. I will show purpose of this method just in a second. Why is this important? And we have already mentioned update method in each controller, which is called on every controller. Here, you would also probably like to have some internal parameters, right? For example, joint names. This is often used use case that you read custom joint parameters because you don't know how the joints are named for each robot, and you want to have generic controllers. You want to exchange them between different robots. Then you have to somewhere store your handles, so you can write and read parameters to hardware. And what is specific or different from other nodes, in the update function, you want to try to keep it short as possible and real-time capable as possible. That's why we developed real-time tools in ROS Controls organization, which provides you some real-time buffering between non-real-time and real-time threads. I will show you in the second where those threads come, where you can see those threads in the controller. Also, also what we would like to have, we would like to subscribe to some topic to receive commands from other ROS nodes, and we would like to publish also some topics, for example, controller state, to see external state in more complex controller, which is useful for debugging and actually understanding what is happening in your system. And for this, always you should also use the real-time publisher, which is non-blocking version of ROS publisher, and it doesn't break your real-time capabilities. So let's see how this looks like in the CPP file. For the shortage of the presentation, we just jump over init method because it's very similar as for the hardware. You initialize memory, you read some parameters. So in the starting, what you always want to do, you always want to read current states from your robot, in this case position. We want to command and store them into next commands, because you don't want to suddenly command 0, and if robot is not in 0 configuration, you would get unintentional movement. Then so do always this, please, in your starting method. Then in update method, we would read some commands from command buffer. We are reading from the real-time thread, so that's why we are using this read from real-time. And then in this simple use case, we will just pipe them further to our hardware. Then when we want to publish things, we are here publishing state of the joint one in our state of the controller. Then we use this structure for real-time publisher, which is then non-blocking structure. And in the callback, what is different for other callbacks you maybe saw in ROS, it's basically that you would here store the data in your command buffer, in your real-time buffer. You would use this right from non-real-time thread. Here is this call is another thread as this one, so you will not block execution of your controllers. And one important thing, which is often forgotten, we would just like to mention it to you because many people have issues with that. Keep in mind that you have to export your plugin search plugin lib. So you have to add these two lines at the end of your C++ file. Of course, here considering your class and what is base of your class, so it can be found. And also you have to create definition, this XML file, which very important controller name. This one name is you will use for dynamically loaded during runtime. And you have to then, of course, export definitions in package XML and CMake list files. So let's see now what is happening. So we defined here array controller because just to show you in a second, it accepts array as input command. So float 64 multi-array we will use for commanding this controller. So let's start this controller. And now let's send some commands to it. So now you can see how robot here is moving. It's moving in the dynamics we defined in our simulated hardware. And you see we reached now the position of 0.5. Also regarding this mentioned state, just to show you that this is also working properly. So we want to get some state from the controller. Remember, we get state from joint 0. Or the first joint, and you see the state is almost 0.05. Of course, this is double rounding here in place, so it's not exactly the same. Okay, and then one important thing here to mention, this kind of controller, this simple controller, they are already implemented actually in ROS controllers package, so we can also reuse those. So let's also start this stock controller here. How we know the difference? We know the difference because you see they have different namespaces, different names, they're accepting the same commands. So if you just want to forward commands to your robot, then you can simply use forward controllers. Sorry. Then you could just simply use your forward controllers already implemented in ROS controllers repository. You see here then the same effect. But now, do not stop in that. Actually, what you want to do when using ROS control, you want to provide some custom commands to your controller. Here we exemplary chosen joint jog command defined in controller messages package, as you see here. Why do you want to do that? Because, for example, here comparing those two messages, you can see here that joint jog messages actually also accept joint names and some more values, which can be useful for your robot. So you always want to use rather more explicit messages than generic messages, because receiving those data here, you don't actually know which joint is meant. And here you can really define this directly. So let's see how we could use custom message in our example. Basically, in the header file, we just changed command message file. And since the displacements here and data here in those two messages are the same type, we can just simply in our CPP file change here a field we are accessing. So let's now start our robot with this custom controller or controller receiving different commands. You see here that command structure is different. We didn't do any additional checks about the joint names in our controller. That's why we don't need them. In some real-time use cases, you actually want to do this. like many controllers in ROS2 control actually do. They check that you are providing data for the proper joint. And what also here enables you, you could actually provide only one data and joint name and then control only one joint. So you don't have to always control, for example, both joints in the same message. So this is flexibility when you are using explicit messages. So I would like to give word back to Bence to give you introduction in ROS2 control.
All right, thank you. Yeah, so now we're going to follow pretty much the same pattern, but with ROS2 and ROS2 control. Luckily, we've explained most of the complex things already, so we can build on top of those. So with ROS2 control, we followed in the footsteps of ROS control, but chose to re-implement the entire framework from scratch to allow for certain extensions that would be very hard to achieve otherwise. We aimed, one of our major goals with the rewrite was to simplify the code base, try to keep things leaner, more approachable by people, and not to rely as much on code injection via inheritance, and just make all approaches much more explicit. So the code should be much more readable and easier to follow. That kind of comes from some of my experience having to answer so many questions over the same thing. So in ROS2 control, the functionalities of the hardware abstraction layer and the robot hardware are separated. The role of the hardware abstraction layer is taken, in this case, by the resource manager, and which can manage multiple sensor, system, or actuator components. These components serve as self-contained hardware drivers, basically each of them being equivalent to a mini robot hardware from ROS control. You will notice that in ROS2 control, we no longer talk about joint handles, but instead we use joint interfaces, or we refer to joint interfaces. All of these interfaces are still single value doubles. State interfaces are going to be read-only, and command interfaces are read-write. But in this case, they're only responsible for a single value. So a sensor component is special because it can only have state interfaces. A system component may have both state and command interfaces, while an actuator component is meant for plug-and-play hardware components handling a single actuator at a time. In the case of ROS2 control, all these components are plugins, so there's no need to re-implement the main loop unless, of course, you have a custom use case and you want to implement your own custom timing. But for the most general use case, we have a node already in place that can work with these plugins, that includes the resource manager, and it includes the control manager as well. So the resource manager here will take care of sensor, system, and actuator components, which all export their interfaces, state and command interfaces to it, as these single value loosely typed interfaces. The loosely typed in this case means that they're still double values. However, the type of them is not set to a fixed set of position, velocity, or effort as it was in ROS control, but they simply have names, which are just simple strings. This way, anyone can introduce their own interfaces with names that are semantically meaningful to them. The system will make sure that only matching things are connected. This setup makes it much easier to implement custom robot drivers for only the necessary bits and reuse existing hardware abstraction layers as much as possible. Similarly to ROS control, the controller manager in ROS2 control takes care of lifecycle management of controllers. However, in this case, we also leverage the lifecycle interface provided by ROS2. So so the lifecycle of each controller is reported through standard means. and the code for handling the state transitions between them, the state transition between these states within controllers, looks essentially the same as any other ROS2 lifecycle nodes implementation. Similarly to ROS control, ros2 control also has a special controller, controller in quotes, which reports joint states. But finally, for ros2 control, we managed to rename this type of controllers, and we started calling them broadcasters. So we have a joint state broadcaster, which, just as in ROS1, its job is to publish joint states, which is then used by the ROS state publisher to create a TF3, so we can end up with a nice RViz visualization. We also have some improvements at the command line world. So ros2 control plugs into ros2's CLI system, and we can query the state for the state of each controller, available and claimed resources. We will show some examples for this towards the end of the Foxy demo. Let me just show you guys the exact same thing, or almost the exact same thing, functionally equivalent to the demonstration I made with ROS1. So this is loading the URDF of the RRBot in ROS2. It is, I'm not going to spend time resizing this window, but this is the same joint state publisher UI. I'm just going to use the randomize button to make this arm end up in awkward positions. So we're going to use the exact same setup for the presentations in ROS Foxy as well. I hope I haven't forgotten to mention anything. If I did, Denis will fill us in. So let's jump back to Denis and have a look at some technical demonstrations.
Yeah, so for implementation of all this flexibility Bence mentioned in ros2 control, we decided to design, let's say, standardized definition of your ros2 control system in using URDF tag. So you would actually, for example, here you would define the type of your system. In this case, we are using system type of the device, which is multi-degrees of freedom device. We decided to call it system and not robot because actually it could be anything with multi-degrees of freedom, also conveyors with multiple motors or whatever other control system in your robotic cell you could think of. Then this tag defines which plugin has to be loaded, so we can dynamically load it using plugin lib, as Bence also mentioned, using the similar structure as for the controllers. And here you define all your interfaces for your joints. So here in this case, we have position, command, and state interfaces for both joint 1 and joint 2 of our RRBot. So here in this example, we picked this fake component generic system. It's not really fake. I mean, it really exists, but it's fake. Fake is that it simulates perfect execution of your robot. And the idea behind this, you just want to fastly test if you set up your URDF correctly, if you set up your parameters of your controllers correctly, your launch files, and you can test now everything without plugging into the real hardware. And I'm currently doing a lot of implementations also for my clients using this generic system, and it helps a lot because I can do it everything offline, and then I just plug it to the hardware, and to be honest, most of the things are working. So yeah, this is a nice improvement we provided there compared to ROS1, where this such a component didn't exist, and would it be not possible to implement it so easily?
4 minutes
so, but now,
to go. 4 minutes to end.
Okay, thanks. So the thing is now let's see how our interface looks like. So we have here RRBot hardware interface. It's a bit more complex because it's more explicit than a ROS1. The most important part is now you have to export your state and command interfaces here so that your control manager and resource manager know which hardware provides what. Also, you can now start and stop your hardware. The idea is here that we can switch the robot in multi-robot systems, start and stop them, or also switch tools. Of course, you also want to store somewhere values. The C++ implementation is basically the same as ROS1 implementation, just of course using some ROS2 interfaces and outputs. And now we would like to use this plugin we designed here. Of course, you have to add all this plugin lib export stuff I mentioned before in ROS1 example. So we would like to use your own plugin. Only thing you have to change in your URDF file, you have to define which hardware interface plugin you want to use. Let's now also jump in the controller implementation. It's also very similar, a bit more methods than compared to ROS1, but the thing is it's more explicit. And now you have to actually define your interface configuration, command and state interface configurations. So controller manager knows to map those to the hardware. Other part with variables is basically the same, using only ROS2 interfaces. So now also, of course, don't forget to export your plugins. Now the plugins are exported in CMake list TXT in ROS2, just important to mention. So now let's start our array controller here and also send some data to our robot. So you should now see we have the same movement as before. This is of course expected, nothing special here compared to ROS1 example. And also if you want to implement specialized controller, you could just change the joint type as your ROS1, and then now you have your specialized controller. Let's start the specialized controller, and I will mention you here CLI interfaces. Now you can also introspect your ROS2 control system using CLI commands. So now I'm listing controllers. You can see which controllers are active in which state, which types are which controllers, and what's their name used when you want to also run them, stop them, and whatever. Not also that, you can also get your hardware interfaces list. And this is important because except listing command and state interfaces, you can see which interfaces are also claimed. So you know this is claimed by some controller, and then you cannot start another controller until those are not released again. So the join state message and the state message are basically the same, but let's just look shortly, provide here join state output. So we should now get zeros out here exactly. And now let's see what happens there when we send also some command. We are sending basically the same command, and you can see now here how join state broadcaster is publishing join state from this what is happening here in the simulation. Okay, now I would give the word back to Bence to give some overview on Outlook.
All right, thanks very much. Yeah, so as a quick recap, so we've shown you guys how to create hardware abstraction layer both in ROS control and ROS2 control, and we walked through a couple of examples for creating and modifying controllers. Hopefully, it's been educational. There's a couple of things that we did not go into details on, but I would just like to briefly mention at the end of the presentation here. So both ROS control and ROS2 control come with a solid set of controllers. They implement the most common use cases for mobile robots, mobile manipulators, robot manipulators, whatever you can think of, really. And a bit of detail before Ricardo cuts me off is, so in this table, top left is the Valkyrie from NASA. It's using a bunch of forward command controllers and their own whole body control implementation. The Husky from ClearPath Robotics in the middle, top middle, is using the div drive controller. Auto Automation's warehouse robot is also using probably a modified version of the div drive controller. On the bottom left, Tiago a wonderful robot, I'm very biased, is using the disk drive controller on the mobile base, a joint trajectory controller for the elevating base, and then another joint trajectory controller for the arm and the gripper, plus another one for the head. Shadow Robot's Shadow Hand, which is an amazing robotic hand, is using, I think, 16 degrees of freedom with the joint trajectory controller to do very fancy and really impressive demonstrations. The High-Q, the quadruped that you can see there by ETH, I hope I'm not mistaken, is using a custom whole body controller, as well as the Talos on the bottom right, which is another humanoid from Robotics, which uses both some whole body controllers and some joint trajectory control setups. Finishing the presentation, I would just like to say that I dropped a couple of references for you guys here if you would like to follow up on anything. So there's a bunch of good documentation resources here. If you are the academic type and you would like, and you work on a robot and you use ROS control for something and you cannot sleep without giving a citation to ROS control, then I put this up here so you can cite this paper. And also, don't forget that all the code of the demonstrations today are in the ROSject. So if you go into the workspaces, you can find everything there. Thank you very much for attending, and hope you were able to follow along.
Thank you very much, Bence. And Denis, of course. Sorry, because and then yes, I couldn't sleep until you mentioned the reference. So thanks a lot. Then let's go for the questions, and maybe we can switch. To the first one. So you know that if you have any questions for Denis and Bence, you can put them here on the questions tab, and I will be asking them the most voted ones. Also, you can vote the ones that somebody else has done. So, Bence, Denis, you are already here. It's one is, I think this is the most voted one, and I think it's interesting because it looks it could show the confusion of people. Okay, so you have shown about changing controllers from ROS1 to ROS2, but here it says Arun Prakash. He asks, there is a ROS bridge available for converting from ROS to ROS2. How different is your method? Who wants to take it?
I can take this one.
Yes, sure.
It's not. So here we presented the ROS control framework as it is in ROS Noetic and the version of it as it is in ROS Foxy. The interfaces, the ROS interfaces of these controllers haven't changed much. The control messages package is a fairly proven one, a fairly mature one, so they're not a whole lot of changes. But I think the main difference between them is not just a ROS plumbing difference. So we did a full rewrite of the framework, and we keep working very actively on ROS2 control to bring a lot more advanced features there that were not really possible with the architecture in ROS control. But I would not say that the architecture in ROS control is bad in any way. It is very, very proven, in fact. But it's just that it's kind of limited to what it is right now.
Mm-hmm. And I think that the Arun, who asked the question, he's confusing the ROS1 topics and ROS2 topics, and ROS, the package, the system of ROS control for ROS1 and the system for ROS2 control package. So you are mixing two very different things, Arun, actually. So the ROS bridge is for translating topics from ROS1 to ROS2, just for translating topics, information. That's it. But here, the Denis and Bence, they are talking about a different architecture that runs inside the ROS system. So it's different. Yeah. Then let me ask you another question by Alexei Merthyakov, that he says, which are the best practices for the debugging problems while writing controllers? That's interesting.
Do you want to take this one, Denis?
Yeah, I can sing songs about that because of last weeks of my work. Basically what I find out, it's really providing good designed state messages for controller, publishing eternal state, and then, for example, using plot juggler or similar tool where you can then fine tune your graphs, because in control theory, you are always somewhat with graphs and plots and stuff like that. Like this, and also classical outputting. I would not say you should have output on the outputting in the update loop on the final system, but during debugging phase, it could be useful also to help you at some point. Although I actually end up writing really nice state messages where I can debug everything, and then it's easier if you can plot this simply.
Are you using, Denis, are you using an RQT console to filter those messages, or just the raw written into the console?
So I'm, actually both.
Both.
I mean, if you need to filter stuff, if you have a lot of messages, you will do it like this. But actually what I'm preferring, using really real-time publisher and then publish your state message. And then you can use the plot juggler. You can just import this message live or saved from the ROS spec, which is very useful if you are also working remote. Somebody can save you all this, and then you can plot all the graphs, because basically often you have to see really closely into graphs when working with control to see why the numbers are not working as you were expecting.
Great. Okay. Thank you very much. Then, guys, we don't have more time for more questions. So I just would like to thank you again for your presentation, awesome presentation, and see you around the universe.